Gases have certain characteristics that are different from the characteristics of solids and liquids. In particular, gases have no definite shape or volume. Liquids have a definite volume, but no definite shape, and solids have a definite shape and a definite volume. These characteristics are related to the molecular properties of the solid, liquid, and gas. For gases, the molecules are relatively far apart from each other and are constantly moving. This explains why gases expand to fill their containers. The molecules move until they hit something like a wall. Why they are compressible. We are simply squeezing some of the empty space out of the gas. And why they have very low densities. There aren't many molecules in any container because they are so far apart. Gases are measured using certain quantities. The specific quantities used for gases are pressure, volume, temperature, and the amount of gas, that is, the number of moles. Pressure is defined as the force per unit area. Mathematically, P equals F over A. Air pressure is exerted by the mass of air above a particular surface. The official units of pressure are pascals, which is 1 Newton per square meter. But pascals are very small amounts of pressure. So when we are working near normal conditions, we use kilopascals. Even then, the normal pressure of the atmosphere at sea level is over 100 kilopascals. Other units of pressure are the bar, which is 100 kilopascals, the torr, or millimeters of mercury, an increasingly rare unit, and atmospheres. Normal pressure at sea level is equal to 1.00 atmospheres, 101.325 kilopascals, 760 torr, 760 millimeters of mercury. Air pressure is measured with a barometer. There are several types of barometers. One old style that you might have at home is an aneroid barometer. It has a vacuum chamber of metal that flexes when the pressure changes. This flexing is converted to circular motion of a needle by a series of levers and pulleys. Mercury barometers used to be fairly common in research and schools. They are more accurate than aneroid barometers. A tube about 1 meter long is filled with mercury and inverted into a pool of mercury. The height of the column of mercury is directly proportional to the pressure. Today, however, because of the toxic nature of the mercury vapor, many states have banned mercury from elementary and secondary schools. The most common barometer today is an electronic barometer. The device has a sensor that generates a voltage determined by the pressure. Once calibrated to the actual pressure, these devices are quite accurate. The gas laws. Beginning in the 1600s, scientists began to investigate the properties of gases. In 1662, Robert Boyle published a paper identifying the relationship between the pressure and volume of air. Jacques Charles discovered the relationship between the volume of gas and its temperature in 1787. Amedeo Avogadro proposed in 1811 a relationship between the volume of a gas and the number of moles of the gas. The ideal gas law arose from a combination of Boyle's and Charles' laws and was first proposed by Émile Clapeyron in 1834. Let's look at each of these laws a bit more closely. Boyle discovered that, if we work at a constant temperature, the volume of a fixed amount of gas is inversely proportional to the pressure exerted on it. Since the volume and pressure are inversely proportional, A plot of the pressure and volume of a gas gives a curve. This gives us the mathematical relationship pressure times volume equals a constant. If we rearrange the equation, we get volume equals a constant times 1 over the pressure, which means that we get a straight line if we plot volume versus 1 over the pressure. Jacques Charles discovered that the volume of a fixed amount of gas under a constant pressure was a linear function of the temperature. Though the absolute temperature scale had not yet been proposed when Charles made his discovery, once it had been proposed, it became clear that the volume was directly proportional to the absolute temperature. So a plot of volume versus absolute temperature will give a straight line. Amedeo Avogadro proposed that equal volumes of gases at the same temperature and pressure had equal numbers of molecules. This is called Avogadro's principle. The concept of the mole had not yet been formulated, but this idea was easily restated in the form of Avogadro's law, which says that the volume of a gas at constant temperature and pressure is directly proportional to the number of moles of the gas. Mathematically, volume equals a constant times the number of moles. This is related to Gay-Lussac's law of combining volumes. We have seen that the volume of a gas is proportional to 1 over the pressure. It's also proportional to the absolute temperature. And it's also proportional to the number of moles of the gas. When we combine these relationships, first proposed by Emile Clapeyron, we get that the volume is proportional to the number of moles times the absolute temperature divided by the pressure. If we insert a constant, the relationship V is proportional to NT over P becomes V equals R times NT over P, or, much more familiar, PV equals nRT, where R is a proportionality constant, the number that makes all the other numbers come out right. This relationship applies to nearly all gases under most near normal conditions of temperature and pressure. The constant R is known as the universal gas constant, and has a number of numerical values, depending on what particular units are being used to measure the values of pressure, volume, temperature, and number of moles. You should note that the number value for the units joules per mole Kelvin and cubic meters pascals per mole Kelvin, or cubic decimeter kilopascals per mole Kelvin, or liter kilopascals per mole Kelvin, which are equivalent to cubic meter pascals per mole Kelvin, these units are the same. This means that the units are interchangeable. There are 3 problems relating to the gas laws on the problem sheet for this part of the lesson.